Partial programs are fast, right? So same as whole programs. They're just as fast. And that's because from day one, we've been loading code and re-optimizing and rejitting and reprofiling as we go. And so people just now know they can add stuff as they go. And as soon as they add more stuff, it'll go through a round of rejitting and reprofiling and things will be fast again. Turns out that this is a hard problem, goes along with my, optimizing compilers are big complicated beasties. De-optimization is a pain in the neck too. It's another big complicated thing inside of JVM. Consistent memory models, another great illusion. All the different hardware platforms I've ever seen have had...
Can I have ask you a question?
Yeah.
What you think about profiling? Is part of the reason that profiling isn't a source of bugs as it is in static compilers is that here it's not used for correctness, right? You don't do, you're doing frequency, right? But like for method invocation resolution, you still have a breakout path in case you make a virtual call, right? So
Yes.
you protect, so in the Java JIT compilation setting, you're protected against a lot more of your decisions.
That protection has its own difficult costs to work around, and that path is also a large, complicated thing that gets taken on a daily basis. So the profile thingy comes along and says, I'm going to do class hierarchy analysis or whatever, and this is hot, I can prove it's static, so I'm going to inline here. While that works for the 99% case, the 1% case times a million people every day means that a million times a day I go to the fallback case. Right, that I failed to optimize, somebody loaded a new class, I had to de-optimize and rejit. And so the fallback cases get tested on a regular basis all the time. And this is something that was different from my experience in sort of the static C Fortran world. When I did benchmarks in static C and Fortran, you didn't have a fallback case, obviously, but also you didn't get to test the whole profile-directed feedback path on a daily basis. It was done to get these spec benchmark scores out, and then a handful of customers turned it on in production, and no one else did. And once the bugs are out of that was it, but no one else could tolerate the risk levels there. That's what I was talking about when I was saying it's the difference between being default production-ready usage and just a funny flag you turn on to make things run faster. And one more thing, just so people know, it's a workshop. I'll talk fast, but you can stop me for questions. It's all good. I like questions, so feel free to interrupt. Otherwise, I'll just plow on.
So my argument is the protection mechanisms that are built into the JIT, not only are they tested,
Yes.
but they're built in. And,
Yes.
And so
Yes.
in the profile-directed feedback work, when you're doing static compilation, the dynamism of what could be happening was hidden a bit. And so then people didn't think through all those cases all the time. And then the
Sure,
way it's run,
sure.
like to do spec marks, the input
Yeah.
doesn't change and all this other stuff that basically don't take you down any tested paths you might
Yes.
really need
Yes.
in a production setting.
So
There's some benefit
Yeah.
to the structure of the VM that helps you get that more correct than you would in the static ahead of time setting too.
I would instead say, I wish I had thrown the slides up here for that one. I put together slides for it, I'm going to have too many slides. Instead, I would say that the benefit here comes from having a QA which it knows it has to test all the off cases. So we have a lot of built-in infrastructure in the hotspot, and I assume other VMs have as well, for helping you test cases which you hope to be rare in the common case, right? But they have complicated bailout, fallout paths, whatever, and so testing that is a major issue. And we have all kinds of funny modes. We put the VM in, and we let QA, rip and rock on them to test out de-optimization paths, de-optimization with an exception, de-optimization returning a long or an OOP or a double or God only knows what all. You have all these weird cases where things are different. And it happens very rarely, but if you don't get it right, somebody will crash, 100% guaranteed, and so QA has to test it. And so we have QA infrastructure geared for wailing away on those pieces.
This just brings up a very painful memory that's sort of relevant. Back when Hotspot was just graduate student code, before it was even called Hotspot, and the students had left, and I was maintaining this thing. We have benchmarks that would run for 3 minutes, and then the optimizations would kick in and recompile them. And 4 times out of 10 they'd get faster, and 6 times out of 10 they'd get slower. Or, you know, sometimes 3 times out of 10 they just crash and produce the wrong answer. And it was because the stuff was all timer-based and non-deterministic, and the code to map the state of the unoptimized to the optimized, or the optimized one way to an optimized another way, had so many different possible inputs depending on where it caught the program and where it decided to inline, that there were places in the compiler that were just plain wrong, where one of the graduate students had used I sub j instead of k sub j, you know, the wrong counter for how many registers are used and can be allocated at this point. And it was one of those, how could this thing possibly work moments that had been working for years and just never tested because it's really, really hard. At least it was, you guys may have figured all this out, but back then it was hard to figure out an exhaustive way to test this kind of dynamically state remapping.
So, right. So we took a page from the suggestions you offered years and years ago, and we have the blah, 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 a lot flags. And so you take all the funny cases and you put a flag in that makes that case happen even when it's not necessary, not needed, just to force the testing mode. And that's what I was talking about. We have all this QA testing. We turn on these funny flags and then wail away at a QA.
Yeah.
De-optimize a lot and inline more or less, or, you know, I don't know, there's like 27,000 of them.
I think this goes right to your point that maintaining this illusion is harder in this,
Yeah.
in this situation.
There are new things that have to be dealt with here that are not dealt with in sort of the static compiler land, new in a lot of different ways. So the whole tracking the program back to, the optimized program state back to its non-optimized state is something that the old compilers never had to do. They had this sort of waterfall model. They took the semantics in and they know they did semantics preserving operations all along, but they had no way to map it back. And one of the things that Hotspot does is it, you know, it's a fully optimizing compiler in all ways, but it will have a complete map back to the original state, but at fixed points. It's not everywhere. So effectively, you'll have to run a few hundred bytecodes before you hit another point where it's lined up against the original Java virtual machine
And that's a
spec
great
state.
achievement, getting that to work solid.
Yeah. And we thank you for pointing us in the right direction on that. Where were we at? Memory models. So all these machines have these different memory models. The rules and visibility of when a load or a store is seen from one CPU to another, they all vary widely from platform to platform, from hardware to hardware. Even within the generations of the same kind of basic machine, x86 rules have varied a lot over the time. Different platforms are more or less aggressive. x86 is very conservative, and Itanium is very aggressive. And then the meaning of your program depends on the rules of visibility. So the program meaning does depend on the Java memory model. And if I don't have the underlying loads and stores match the Java memory models, your program meaning changes, your program is wrong, or my JVM is wrong, my JVM is not faithfully implementing your program, right? So we have to match the Java memory model on all these widely different platforms. And pretty much none of them match the Java memory model, right? There's no, I got it for free on any of these pieces of hardware. So the JVM is bridging the gap on the memory model itself. And the trick to that, of course, is you have to bridge that gap while keeping your normal loads and stores fast, right? That's the hard part. How do I ensure correct visibility rules while not like fencing every load and store on the planet? That would just be like death. So there has to be some rules on what it means to have loads and stores be visible, and then when I have to bridge some kind of gap, there's some fences, or there's code scheduling rules, or there's placement of locks and CAS-ops in the right kinds of places. This in turn requires close cooperation from the JIT. This is not something that the JITs normally like to do. They like to go schedule, and they take, sort of CPU direct data dependencies, and outside of that, you can schedule freely. The answer is no, you cannot. There are scheduling barriers in the JIT having to do with memory model rules that have to be, like baked in, like a Java memory model is baked into the JIT's brains, right? And then, as an implementer of the JIT onto a new target platform, I have to have detailed knowledge of what the hardware's memory model is to know when I have to fence and where I have to fence and how often, when I can allow things to float around and when I can't, that kind of stuff. Sort of hand in hand, you get this different thread models. And And so you get consistent threading provided by Java. That is, in Java you just say new thread and it just works. But under the hood, you're going off to AIX or Solaris, so you're setting thread priorities, or you've got cell phones, or heaven forbid, like the cell things. Micro devices to 1,000 CPU machines, and it all just works. And to make it all work under the hood, there's a lot of work that goes in to make these threading models just like magically come together. Like, wait, notify don't have direct implementations on these different OSs. You're down to semaphores or locks and blocks or whatever. The different OSs provide different ways that you do synchronization, and you have to figure out how to jam wait and notify on top of that. Locks are fast. This is an interesting observation here because what it did to the programming community as a large. So contented locks are obviously block and they go to all the OS and Amdahl's law and slow and blah, blah, blah. Although you would love to have fairness from the OS. And that was another issue that would typically did not happen when the locks got extremely over contended on a particular lock. The OSs were not fair, and the Java programmer sort of expected them to be fair, and then you had thread starvation, and that was on and off fixed at various times by hotspot and not fixed by hotspot, and different revs do it or don't do it accordingly. It's one of the things I think belongs in the OS. If I'm going to be context switching between 1,000 different guys who all want the same lock, I would like the OS to guarantee fairness. Fine. But if you're not contended, the locks are down to like a dozen nanoseconds or so. They're really fast. And in some cases, like with bias locking, it might even be faster yet, 1 or 2 nanos, right? So these are very fast user mode locks. They provide all the guarantees of a lock while being really, really fast if like no one cares. And why do they get optimized? It's because synchronized is so common. So let's look at this dynamic here for a second. People don't know how to program concurrently right now. Now, they didn't 10 years ago for sure. So when I say people, I mean millions of programmers, right? And so people got into the, well, just add locks until it works mentality. I don't understand some race condition, add another synchronized, add another. Okay, eventually it works. Oh, yay, it's the lowest common denominator of concurrent programming, right? So locks became insanely common. And if you look at the forums and what was going on in the Java 1.2, 1.1 days, locks were a major issue. Locks were slow. So JVMs optimized them. And because locks became fast, this style of just add locks until it works lets you make progress. You could write concurrent programs, a particular horrible style of concurrent programming, but you could do it. And so, as an industry, we got 1 million people to write in this style, and we learned a lot about concurrent programming. Like, we learned that this style sucks. But we didn't know that until locks became cheap enough that 1 million people could write this way and figure out that that's, what they could do. And then we all realized, like, we handed these people this horrible idiom for concurrent programming. All right, fine. I'm done with that rant.
I'm going to use that quote in my talk.